Good afternoon, everyone. We start with the afternoon session of the symposium, and Professor Atsushi sorry, will talk talk about a simple two-dimensional model for the Hawking radiation. So it's a pleasure, Atsushi. Thank you.
Well, thank you, Rafael. So thank you for inviting me and giving me the opportunity to speak here. And today I want to just talk about a very simple two-dimensional model, which is obviously not very realistic, but I think it will help in understanding how Hawking radiation comes about. And so that's a talk for today for me. Now, well, this is probably almost everybody know this, but a black hole is an object formed, for example, by gravitational collapse of a large star. And in classical physics, nothing comes out of a black hole, and even light can come out from the black hole. But yeah, actually, it's now 50 years ago, so probably most of you haven't been born at the time. Actually, I read it, I think, in 1980 something, 5 or something. Anyway, so Hawking discovered more than 50 years ago that in quantum field theory, in curved spacetime, a black hole of mass m radiates like a black body temperature, called the Hawking temperature, obviously, and that's given by this formula. And Kb is a Boltzmann constant, and yeah, h bar is the Planck constant, and g is Newton constant, and c is named after somebody called light speed, so light speed constant. And for a spherical symmetric black hole, which is unrealistic, I think, these days. But anyway, if there's a spherical symmetric black hole with 30 solar mass, then the temperature is very small. And actually, wavelengths of a typical Hawking radiation is Schwarzschild radius of the object. So it's very low energy. And I tried to study Hawking's radiation, Hawking derivation several times, but it's very difficult. And he derived his radiation for a spherical symmetric black hole, it's not realistic, but other than that, his model is very realistic. And it involves sophisticated use of mathematics and quantum field theory in curved space-time, and some actually unreasonable idealization. And that makes it a bit difficult. And then also, obviously, the space-time is time dependent, and that's obviously realistic, but that makes calculation very difficult. And so the thing is that you start from almost a flat space-time and then evolves to black hole space-time. So it's very difficult to treat such a thing exactly. And my question, I'm lying a bit because I did this. I studied this model and came up with the rationale. So this is the rationale. So is there a simple model allowing exact calculations but still capturing the essence of the Hawking effect? So that you could ask such a question. And what I came up with, perfectly reflecting collapsing spherical mirror. So it's like let's assume spherical car or something, but it's very simple to deal with. And so we use, as usual, quantum field, which is massless scalar field. And so you imagine a perfectly reflecting spherical mirror of mass m sitting at some radius larger than the Schwarzschild radius. And then suppose this scalar field is in the vacuum state without any radiation coming in or going out. So that's reasonable because it's very unphysical to assume ingoing radiation or incoming radiation from the beginning. And this vacuum is called the Bolwer's vacuum. I don't know how to pronounce this properly, actually. Volvia vacuum. And so that's the initial sort of setup. So there's a perfectly reflecting spherical mirror, and the scalar field is in the vacuum state. And then suppose the mirror starts collapsing at some time in a spherically symmetric way, so that calculation can be done, and disappears below or away from inside, actually disappears inside this Schwarzschild radius. So that's the model I would study, but that's still too difficult for me. So yeah, well, yeah. So yeah, before that, actually. So sorry. The advantage of such a model is the following. So the space-time outside the mirror is static, spherically symmetric space-time with black hole of mass m throughout the mirror collapsing, because there's this theorem called Barkov's theorem. So if space-time is spherically symmetric, even if it's collapsing, the space-time has to be Schwarzschild space-time. So it's very easy. So therefore, this problem would reduce to finding out the evolution of the quantum field state with a reflecting boundary at some point, time-dependent boundary radius, and with the initial condition at some time being this Boolean vacuum with no particle emanating. And I sort of prematurely said the thing, but it's still a bit complicated, mainly due to the scattering by the space-time curvature. So even if black hole emits a particle, then it can sort of bounce back because of the curvature. So let's well, since we already abandoned this realistic, so gave up on being realistic. So let's just go further away from reality, and let's go to two dimensions. So, if you go down to two dimensions, actually there is no scattering for massless scalar particle in any space-time. So for massless scale, we'll see if you don't know this. I'll tell you why. In two-dimensional massless scalar field just goes to the left or go to the right. In this context, goes out or goes in, and there's no scattering. So it's a very simple setting, and the only time the scalar field scalar particle changes direction is when it hits a mirror. So that's a very simple situation. So we study a two-dimensional analog of quantum field theory of massless scalar field bounded by the perfectly reflecting collapsing mirror, which actually is a point because they are only in a one-dimensional space. So you have a point, and that's reflecting everything out, and so this particularly reflecting collapsing mirror. So this is which is a point, and so with the state again, the state is the scalar field which. Sorry, the state is the scalar field is the Boolean state, Boolean vacuum with no particle present. So that's the setting. And the plan is the following. So I just have to do a quick review of two-dimensional Schwarzschild spacetime in so-called Kruskal-Sekeres coordinates. Yeah, this is mainly really for people who have already known this thing. Just to remind you some important things regarding this talk. And then we review massless scale field in two dimensions. And as I said, you see that there's an ingoing field and an outgoing field, and they are just separate from each other. They don't interact. And then I have to talk about stress energy tensor. And unfortunately, in quantum field theory, the stress energy tensor is infinite. So we have to have some way to come up with some finite stress energy tensors to study energy flow and so on. So that's so I review that, and in particular we discuss renormalized stress energy tensor in this Volvier vacuum and something called Hartle-Hawking vacuum. And then finally, if hopefully I get to this, we talk about renormalized stress energy tensor in this perfectly reflecting collapsing mirror. And you find that energy flux consistent with thermal loss of temperature kappa over 2 pi. Somehow this combination of temperature comes up very often. So from the beginning I say kappa over 2 pi. So we find that energy flux consistent with the thermal loss of this temperature with kappa being 1 over 4m with every constant set to 1 is seen to go out to infinity at a later time. So that's what we find. Hopefully, if I don't run over time. And I have to apologize because I in the abstract I was very, very ambitious, and I was going to say that, oh, actually, you show that this is a thermal, really thermal state. But in fact, what I show, what we find is that energy flux, just a number, is consistent with thermal burst of temperature, this temperature. So if you just look at the energy flux, you don't really know the content of the flux. It could be a monochromatic wave coming out, but from other things, we know that it's a thermal burst. So anyway, at least we know that energy flux are consistent with the thermal burst of temperature. This temperature is coming out. And but I apologize that we only so we only show that total flux equals that of a thermal burst of temperature, this temperature. So that's the plan. Okay. Let me just do a lightning review of Schwarzschild space-time. So I decided to go backwards from classical to usual Schwarzschild space-time to save time. So this is the Schwarzschild space-time, two-dimensional Schwarzschild space-time with so-called classical Sekeres coordinates v and u and v, and so large U and large V. We'll later see small u and small v, but large U and large V are called classical Sekeres space-time, and this region with V positive and U negative is the outside region of the black hole. So we live here, and this region is black hole space-time. So if U is positive and V is positive, it's a black hole region. And since we put the mirror here, and so we have mirror here, so everything here is irrelevant. So the light rays reflected by the mirror this way, some going into reflected to infinity, and some going into the black hole. So only I guess V positive, so large V positive region here is relevant. And anyway, so in this coordinate system, the metric goes like this. So it's proportional to du and dv. That means that u constant line and v constant line are null geodesic. So u constant line. So u is going this way. So this line parallel to v axis is the outgoing null geodesic. So outgoing light ray is relevant. So u is the variable relevant to the outgoing null rays, and that's the important thing we'll look at. And v, on the other hand, is the ingoing. V is relevant to the ingoing light ray, and if v is constant, then the line is like that. So that's ingoing. And And also R is determined by this relation of R and U times V. So R is a function of UV. And so actually this coefficient in front, called conformal factor, is should be regarded as a function of large U and large V. And the horizon, for horizon are V equals 0, sorry, U equals 0 line and V equals 0 line here. So you have past horizon and future horizon, and we'll put in some mirror later. So the past horizon is hidden, but the future horizon is exposed. And so anyway, so the important thing is, one of the important things is that horizon, future horizon actually, is at U equals 0. And we are in the U negative region, and if a particle goes into the horizon, the particle large U of the particle becomes positive. So that's one thing possibly to remember. And so in this picture, the red curve. So if R is constant, then U times V is constant. So it corresponds to they correspond to hyperbole, and if V over, so if T is constant, V over U is constant, so time constant lines are sort of this straight line like this, and so this, when you send T to infinity, then you end up with this horizon, and so that's thing you want to note. And the singularity is that UV equals 1, but you don't have to worry about that very much in this talk. So now we introduce a pair of coordinates which are important in this talk. So as I said, the black hole region is well, in both regions actually, black hole region and outside region, V is positive, but this U changes sign. So U is negative outside the black hole, and U becomes positive inside the black hole. And if you are only interested in the region outside the black hole, you can parameterize, you can write large U as minus E times minus kappa U, where kappa is 1 over 4m. For a good reason, which I'm not really explaining. So why you multiply this by kappa is a good question, but I have no time. I'm not explaining that, I think. And V is positive in the outside the black hole, so you can write V as e to the kappa V. And if you use this small u small v variables, then they are related in a more straightforward way to usual time and usual radius, like that. And R star is called the torus coordinate, and so in this expression you see that U, constant U line, is certainly outgoing null geodesic, and constant V line is an ingoing null geodesic. And in these coordinates, the previous what we've seen, this one becomes that. So where the metric, so I'm using plus minus convention, which probably is different from what you do, but anyway, so in plus minus convention, this is the metric. So metric is proportional to du, small du, small dv, and C is again a function of small u and small v, but in terms of R, it's written this way. And this is beginning to look more and more like a usual Schwarzschild space-time. And in fact, if you plug this form, plug this expression for U and V, then you get the usual Schwarzschild space-time. And this expression, which you usually don't see very often, is very important. So so we use this du and v, which are called Eddington-Finkelstein coordinate, and u, because of this expression, if well, important thing is that if send u to infinity, then you hit the horizon where large U is 0. So U, as U, too many U's, right? as U increase U, this small U, then line of constant U sort of accumulates towards the horizon where large U is 0. So that's one thing probably good to remember. So this is what I said now. Okay, so that's a sort of lightning review of Schwarzschild spacetime. Any questions? You all know that, right? Okay, so let's look at the massless scalar field. So we look at the massless scalar field in this general sort of spacetime. One example is this Schwarzschild spacetime in Eddington-Finkelstein coordinates. So we just allow GUV to be a general function. And in 2 dimension, for field equation, it turns out that this function is irrelevant at all. So it's not relevant at all because for any g, the field equation just becomes this equation. So if you differentiate scalar field with respect to v and u, then it's 0. So the general solution is the following. So if the function depends only on u, then this is killed by the v derivative, so it's a solution. And if the function is a function of v, then it's killed by this u derivative. So this is a general solution. And therefore, the field, you can just separate the scalar field into outgoing and ingoing fields. So these are just totally separate things, and we concentrate on the outgoing field in this talk. And yeah, basically, if once you declare that the function is just a function of u, then that's a solution. So in a way, there's no field equation to solve in 2 dimensions. And so as I said, f of u of any, so for any function, f of u is a solution to this equation. Right, so let's say, let's study massless scalar field in Schwarzschild spacetime in the this Eddington-Finkelstein. So in this representation, so we are only talking about the field outside the black hole. So since in fact the metric is totally irrelevant, so this doesn't appear in the equation, we can pretend that this is not there when you quantize this field. So that's what you do. So you just say it's a function. Basically, you just Fourier transform this, and you call this positive frequency mode and negative frequency mode. And maybe I told somewhere that yeah, for the ingoing field, because of this dependence on t, u is actually the small u can be thought of as a time for the outgoing field. So you can, so if u goes to infinity, that means that time goes to infinity. Okay, so this is like really the usual quantization since e to the minus I omega u can be written as e to the minus I omega t times e to the minus omega r star torus coordinate. And it's, after all, proportional to e to the minus I omega t. So that's what you do when you quantize field theory. And so this is sort of a straightforward quantization you do. And, well, you can forget about these factors. And then we define this very natural vacuum state by saying that, which is called a Bohr vacuum state, and you require that state be annihilated by the annihilation operator. So that's all you do. So that's a Bohr vacuum, and so in this state, no particle is there. So this is a no particle state with respect to the usual energy because we are using the usual time. And let's recall that large U, this small u is related to large U this way, and kappa is 1 over 4m, and actually called the surface gravity. And again, as u goes to infinity, so for infinite future, for an ingoing null geodesics, they just accumulate to this v-axis, which is the u equals 0 line. And so maybe this is a very, in a way, for looking from this global picture, this is kind of unnatural because this oscillates infinitely many times as it approaches the horizon. Okay. So that was one way you can come up with a state in a short space time, but there's another way of getting a state. So in this we use the global short spatial space time, and going back we had this. We started with this, and this is a function of large U and large V, and U and V are just global coordinates like that. So you could do the same thing, and as I said, in this scalar quantization, this factor doesn't matter. So in this space-time, again, you can have a outgoing field, which is a function of large U this time, and so this field is expanded this way, and then the Hartle-Hawking vacuum is defined as a state which is annihilated by this annihilation operator. And since this function is totally different from the previous function, e to the minus I omega small u, this state is different from the Bohr vacuum. And so our interest is, well, this is already known, but let me just review later that we'll find that the Hartle-Hawking state contains energy fluxes consistent with thermal flux, thermal mass of temperature kappa over 2 pi relative to the Bohr vacuum by studying the renormalized stress energy tensor. So that's what we'll do next. And again, we are not really talking about the spectrum of the flux. We're just looking at the total value of the flux. So let's do a very again lightning review of stress energy tensor. So stress energy tensor in the with the usual definition is like that, and then for this space-time, something this becomes very simple, and u component becomes just a second derivative of phi, and since the only part which depends on the on u is the outgoing part, so TUU is the second derivative of the outgoing field with respect to, sorry, not secondary, sorry, first derivative of outgoing field squared is TUU, and TVV is the derivative of the ingoing field with respect to V squared. And if you put in UV, then it just vanishes. So TUV is 0. And this is related to the trace of the stress energy tensor. So if you take the trace of the stress energy tensor, then in fact it's proportional to TUV. Recall that the metric was off diagonal. Metric is had only off diagonal element, so only GUV is non-zero, and basically the trace is turns out to be proportional to TUV, and so the trace of the stress energy tensor is 0. And I'm not explaining this again, but this is a consequence of scale invariance. So the theory is invariant under scaling phi by some function, and it's a consequence of that. And TUU can be regarded as the outgoing energy flux. So TUU is sort of outgoing energy flux along the analgesic going this way, and TVV is the ingoing energy flux. So, and then let's look at the stress energy tensor in quantum field theory. So again, outgoing field is expressed this way, and say you take any state satisfying this condition. So somehow when you square this and when you square this and take the expectation value, we assume that there's no term A, or actually by taking the Hermitian conjugate, A dagger term is 0. So with that assumption, and this assumption is satisfied by the vacuum state and the thermal state, so we are not losing much in the context of this talk. And so if you do that, then since this is just so this is just this expression. So you can simply calculate this, and you end up with this expression. And then there's this term, a dagger term, and to make this the same as this term, a dagger a term, you use this commutation relation to do that. And by doing that, you end up with this term. So you have a dagger a ordering, but you have this term, and this is a famous zero point energy. And what you do usually in flat Minkowski spacetime is just getting rid of that. So by so-called normal ordering, and so for two-dimensional Minkowski spacetime, what we do is just we replace this. So in this, well, I changed the small a to large A because small u turned into large U and small v turned into large V. So anyway, so in this spacetime, in two-dimensional Minkowski spacetime, we just drop. We just drop this term coming from basically this term. So we just say that, oh, okay, actually, we just assume, not assume, but we just replace this a dagger combination to a dagger a combination, and so therefore, as a result, you get rid of that. And yeah. So then clearly, since the order is a dagger a, you in the vacuum state defined by saying that that state should be annihilated by an annihilation operator, you get 0. So that's good because we kind of know, I suppose, we want to. Well, I guess we want to input the fact that you don't see any energy in the vacuum state in Minkowski space. So we do that, and then well, the object of our interest later is thermal state. So in the thermal states, you can evaluate this yeah, with this assumption. So A dagger A, expectation value of A dagger A is, I'm cheating a bit because this is a mixed state, but pretending that this is a pure state, then this expectation value is of this form. And this maybe people who learned thermodynamics or statistical dynamics, I suppose, this doesn't look like a thermal state, but this is, if you put in h bar and Boltzmann constant, then this is h bar, which h bar omega, which is the energy of a particle, and kBt temperature is kB times temperature. So this is e to the energy divided by kBt. So this is the thermal factor. So anyway, so for thermal state, yeah, it's a bit awkward because of the continuous nature of omega. We have this delta function, but other than that, well, people who learn statistical mechanics would be familiar with this, I think. And so anyway, so by putting in this into there, you get this value, k squared, kappa squared over 48 pi, so 48 pi, sorry. So maybe this is something to remember. So this is the thermal flux, the flux of energy if the outgoing particles are in a thermal state of temperature kappa over 2 pi. So that's something which comes up later. Now, so for general state, so we know how to how to renormalize the stress energy tensor in Minkowski space time. But what about this space time where field looks exactly like that? And maybe at this point, it's good to introduce some name. So this state, 0C, annihilated by the A omega in this space-time. Let's call this conformal vacuum for the conformal factor C. So that's the name I gave this state to this state. So now the temptation might be that we just do the same thing. So we do normal ordering, therefore the stress energy tensor is 0 for this vacuum state. But it turns out that if you do that, it's somehow inconsistent. So we have to do something else. And so what we do is so-called point splitting method to define this. So the thing is that, so if you, instead of partial u phi squared, which turned out to be infinite, if you just consider partial u phi at u1 and partial u phi at u2 not multiplied together, then it turns out that you get this expression. And so now if you make u1 and u2 coincide, then this is clearly infinite. But what we do is, since we decided that this thing should be 0 in Minkowski space, we in spite of the fact that this was infinite to start with, we just subtract the flat space equivalent of this expression and take the limit v is going to 0, and then we are actually left with a finite quantity. And let me just do this very quickly. So for in this space-time, we define the following variable s, which is obtained by integrating this conformal factor with respect to u. Then, of course, partial s partial u is c. And it turns out that this quantity obtained by integrating c over u, it turns out that this is affine, so-called affine parameter. And yeah, people in the know perhaps. So affine parameter is sort of equivalent to flat space when you discuss these things. So what we do is we basically subtract the point split version of TSS with this coordinate. So we just subtract this expression from the original one, which is actually this one. And but actually, you can't really just subtract this thing from that because this is TSS rather than TUU. So to convert this TSS into TUU, you have to put this things by basically a chain rule. So if you do that, then you can subtract this from that and take the limit u1 goes to u2, u1 and u2 goes to some number, some u, and then this one's you can, people who are very good at mathematics can see that these more singular parts cancel maybe, but if you don't, then don't worry. I claim that actually you are left with some finite thing, and you are left with this quantity, this expression. So renormalize TUU is this, and renormalize TVV is that. And a strange thing is that we saw before that TUV is 0 classically, but if you set TUV renormalized to 0, then it would conflict with the conservation equation for the stress energy tensor. And if you look at the equation for the conservation of stress energy tensor, then given these two, the unique solution turns out to be that. And it also turns out that if you take the corresponding trace of the stress energy tensor, then it's 1 over 12 pi r. R is a scalar curvature. If you use a different convention, it's minus 1 over 12 r pi r, but it's either that or minus this. And since we classically we started with 0 TUV, and somehow quantum mechanically by, in our case, calculating TUU and TVV and imposing this condition, we came up with some non-zero value. This is called the trace anomaly. So this is anomaly, quantum mechanical anomaly, and people who wonder, oh, why should space-time has R, but actually it's in 2 dimensions, so actually R is non-zero. So we have this anomaly. Now we use this magic formula to find the stress energy tensor for ball-ware vacuum. No particle state in where's ball? Yeah, here. Is that right? Yeah. So we use this formula, this formula in particular, to find the ball-ware TUU. Actually, sorry, this is renormalized. So renormalize TUU and renormalize TVB are both equal to that. And interestingly, if you plug in R equals 2m, this is equal to minus kappa squared over 48 pi, which is exactly the negative of the the energy flux corresponding to thermal flux of kappa, temperature kappa over 2 pi. And clearly you can see that at R infinity, it's 0. So somehow, if you take this TUU, then you start from negative flux corresponding to negative of thermal flux of temperature kappa over 2 pi, and gradually gradually becomes less negative, and it becomes 0 at infinity. And on the other hand, this TVV, the energy flux corresponding to ingoing null rays. So it starts from 0 at infinity, and then at the horizon, this becomes a negative of the thermal flux of temperature kappa over 2 pi. And yeah, this is something to remember actually. So for the Boole vacuum, the TVV, we don't deal with TVV very much, but this is important later, right at the end. So TVV, the energy flux of ingoing rays. So ingoing state has a negative flux into the horizon corresponding to the temperature kappa over 2 pi. So that's something to remember. Now, before talking about the Hartle-Hawking case, let's discuss general vacuum for the outgoing field. So suppose we define this curly or calligraphic U to be just some function of f, uf, and large U equals minus e to the kappa minus kappa u is a special case of that. So then you just take the conformal vacuum state corresponding to this quantization. And then since small u and this curly u or calligraphic u are related by just, yeah, I should have written this there. So d large u, d calligraphic u is f prime du times small du. So this thing becomes that, and this is equivalent to having a conformal this conformal factor, and using that you can actually calculate this renormalized TUU, outgoing energy flux in general. And doing so, it turns out nicely that for this conformal vacuum state, the outgoing flux is the one in the Boole vacuum plus this expression where F is just that. So then for Hartle-Hawking case, this F is e to the minus kappa u. So you just plug this in, and people who are good in math can immediately see that you just get, I think, 3 kappa squared minus 2 kappa squared. So you get kappa squared over 4 pi. So Hartle-Hawking vacuum is a state where energy flux, outgoing energy flux is Boole plus this, and similarly, ingoing flux is Boole plus this. So since for the Boole vacuum, this part becomes 0 at R infinity, in the Hartle-Hawking state, there's a constant flux of energy. This energy, which is energy flux, this corresponds to kappa over 2 pi temperature. So in the Hartle-Hawking vacuum, there are ingoing and actually also outgoing fluxes consistent with the thermal fluxes, temperature kappa over 2 pi. And then the question I have to ask, we have time. What happens if there's actually, again, static mirror reflecting the field at some radius, and the state being a Boole vacuum? And suppose it just starts collapsing, and then what happens? And falls into a black hole, what happens? So that's a question. And we actually calculate, yeah, so let me just explain again. So trajectory mirror is R equals R naught. In other words, UV, say UV equals -1 or something. So this is the trajectory of the mirror. I didn't draw it very well, but trajectory mirror before it starts collapsing. And this sort of maintains the Boole vacuum. So the static static mirror is a sort of holding the state to Boole state with no particle state, and then it just gives way to maybe the black gravitational, nuclear reaction ceases to exist, and the mirror starts collapsing, And suppose it has this equation, V equals Fu. So if you look at this way, look this thing this way, then if the mirror is collapsing into the black hole, then the V intercept, which is obtained by U equals 0, so F0 must be positive, and also F prime 0 must be positive, because yeah, so it's increasing as U is increasing. So so we just impose this condition to guarantee that the mirror falls into the black hole like that, rather than going like that. So the mirror falls into the black hole after this point, and then now let's so we can actually play the same game as before. Now the ingoing state, which we didn't discuss much, is in the Ball-Ware state. So it's like that with this Eddington-Finkelstein ingoing coordinate V, where the vacuum is annihilated by annihilation operator. So this is, yeah. And then the thing is that we can impose a boundary condition there, so that V variable here, say large V variable. So in this mirror line, the V variable, large V, is related to large U like that. Therefore, large V, small v, is related to small v U like that. And therefore, V, small v, is, which we call Fu for obvious reasons, is given by like that. And then basically, this gives you a map from V to U. So this function, basically this function, turns into minus I omega Fu. So that's what's happening, because that's the mapping between V and U here. And so therefore, after the field is reflected by the mirror, so imposing appropriate boundary condition, the field becomes that. So just V, small v here, is replaced by oops. So this should be deleted. Sorry. Yeah, I don't know. This should be deleted. Anyway, so small v is replaced to this round or calligraphic U, where it is given by F of U. Like we saw, large U was equal to that. Now this curly U is equal to this. Then you can play the same game. So this state with the falling mirror spacetime should have this energy flux, which is a Ball-Ware one plus this. So it's the same thing. And using this formula, we find that F dash U is well, you can probably do that yourself, equal to that. And near the horizon, for large U, this is so large for large small U, this big U is very small. So you can replace this. Yeah, so you can replace minus U by e to the minus kappa U, and this by a constant f dash 0 over fu, which was assumed to be positive. And sorry, then you can calculate this f dash u and triple derivative u like that, and plug this into there, and lo and behold, the state obtained by in this space-time for large user, future is indeed the Bolwer case plus the this thing consistent with thermal flux of temperature k over 2 pi. So yeah, so I should say most of the thing I said probably can find any like in textbooks or papers, but probably uh, it, maybe it wasn't sort of assembled. Those things weren't assembled this way before. Anyway, so what I showed is by considering a collapsing mirror in two-dimensional space-time, we have a very simple model of the Hawking radiation with outgoing energy flux approaching to kappa squared over to 4 pi, 48 pi. So which is the energy flux for a thermal bath of temperature kappa over 2 pi. And transition time is like actually 4 times m in sort of natural units, and it, it's it's like it's of the order of short light traversing time of the short radius, uh, and it's very short even for large black hole. And I didn't say this in this talk, but actually, if you yeah, so I said this actually, yes. So energy flux going out to infinity is this quantity, but I said that energy flux going into the horizon is this quantity because um, the energy going into the black hole actually is not changed as from the black ball wave vacuum. So these are equally balanced. So there's no energy created in a way. So energy is going to infinity, but also negative energy is going into horizon. So although we use this collapsing mirror to derive this effect, somehow at later time Hawking radiation. So this collapsing mirror has almost nothing to do with uh, uh, Hawking radiation, and somehow I think sort of pair creation type picture is more appropriate, probably. And finally, yeah, I don't know if I'm really taking this further, but I think it will be interesting to examine the quantum state in more detail rather than just the expectation value of the stress energy tensor to find exactly what's happening in the transition period, although it's very short. So, and maybe it's interesting perhaps to extend it to 4 dimensions. So that with that, I'll finish.
So, any questions?
Okay, so thank you very much, Tsuchi, and it's also very good to remember things we've already seen. So don't worry about the revision material. I was wondering, it's just a curiosity. So I mean, you could have here a model where you have your mirror, it starts collapsing, but it doesn't fully collapse. So it stops before it actually creates a black hole. So in that case, the vacuum state will still change, I guess. So yes. So there is no particle creation in that case. Oh,
Oh, it's a key. So somehow uh, this point is kind of this one. Yeah, maybe yeah, this if we stay like this, then there's no problem to this, and
there is no particle creation.
maybe
Not steady. But there would be a particle creation. That would be my guess. Some particle creation because the vacuum changes. So it's a kind of because it could be interesting to see precisely, how that changes as you would approach the horizon in the end point. of course, you would need some very physical matter in the mirror to act, but just as a proof of concept, because it seems that the formation of the black hole would be fundamental for having a thermal spectrum and the Hawking radiation, of course. But there's still a Bogoliubov transformation from the initial to the final vacuum, even if it doesn't get to the point of collapsing.
I think my guess is that if it just mirror collapses and stops, then it's still supporting some kind of Boltzmann state. So I think there's no particle.
The space-time is still short.
Yeah.
It's still Schwarzschild outside, yes, but there is no horizon.
There no.
Not at all.
Yeah, that's my guess, but we can look.
Okay, so maybe that's an interesting.
Yeah, maybe. Yeah. Thank you. Thanks for asking.
May I ask another question? Yes. So you said in the beginning it's a reflecting mirror, and but maybe I just missed it. So how important was that? Where did you use it? And yeah, so these two things. How important was that it was a reflecting mirror rather than partially absorbing? And where did you use it?
So I think it makes the mathematics very simple. So if this is the reflecting mirror, everything is reflected like that. So this map between V and U is exact. So it just to make things just easy. Yeah, but if it's a partial reflection or something, I think it's still so somehow the picture of I'm not really familiar with this derivation, but I think people derive it by other particle pair creation in the gravitational field, and the balancing of the stress energy, balancing of the energies kind of suggests that that's probably the right, well, I don't know, more physical picture. And at the end of the day, probably collapsing things is irrelevant, perhaps. And maybe that's something to investigate, but yeah.
The reason why I was asking is that, well, I mean, in classical scalar fields, if you impose a reflecting boundary condition, is not a boundary condition; it's a family of boundary conditions. So you could have, say, a Dirichlet, or mixed,
so this
or Neumann, and you can get different things depending on what you choose precisely. So.
Yeah, I think in this one, if the reflection, so I use a very naive one, just the value of this past. So the value of so this function just turns into fu. So that's what so I think this probably corresponds to Neumann boundary condition, but I'm not really sure actually. So
Okay.
Yeah.
But if you impose, say,
Dirichlet, I think if you do Dirichlet, then just this. Yeah, that's an interesting one. So
in that case, the scalar field should vanish or something at the mirror. That should be it. So there's a relation then between.
Yeah. So So when people do a reflecting mirror calculation, they use Dirichlet, and well, I was just assuming that for Dirichlet condition, things are not different by much, but I'm getting unsure. So
I'm just curious because
I think it's the same, but
okay.
I'm not sure.
And then you could have mixed, boundary conditions, and because in classical fields sometimes you get different results depending on exactly what you choose. Anyway,
well, thank you very much.
Thank you. Any further question? Carol?
So I was wondering about the Casimir effect.
Oh.
Does it play any role here, or maybe it's not relevant?
Which Casimir? So some people call you mean dynamical Casimir effect, or?
Yeah, because you have a collapsing mirror, right? So you have a.
This is I think this is exactly the same as that. So this is if you look at this situation using the small UV, Eddington Finkelstein coordinates. I think what's happening is that the mirror is sort of moving like that, and that's exactly what you find in Beryl and Davis, actually, the particle creation. But I think if you can do it that way as well, so it is that dynamical Casimir effect. If you
So it's equivalent.
yeah, I think so. Yeah.
Thanks.
Thank you.
So I think if anyone has further questions, we can ask Atsushi and during the week. So let's thank Atsushi again for